So, welcome everybody. Now we are officially starting with this webinar talking about spark ablation as a building block for nanostructured multifunctional devices. I'm Leandro Sacco. I'm application specialist at VSPARTICLE, and I will one of the hosts and the presenter of today's webinar. Please give me some signals that you are listening properly this presentation. Yeah, okay, so I have few feedback, thanks to the audience. So our guest today is Professor 𝐕𝐢𝐥𝐤𝐨. So please, 𝐕𝐢𝐥𝐤𝐨, say hi to the audience and say a few words from your side.
Say hi to the audience. So hi to the audience. I'm 𝐕𝐢𝐥𝐤𝐨, and you will be hearing a little bit more from me in a few seconds.
Okay, 𝐕𝐢𝐥𝐤𝐨, I know that you are there. So anyway, I will go through the agenda. In today's webinar, we will learn about the possibilities about spark ablation and impaction printing for conducting systematic research and pioneering developments in new and novel materials. So I would like to give you an overview of the agenda. So first we will talk about the introduction about VSP, basically who is VSP as a company. We will provide a short bio of the speakers. Then we will move on with the presentation given by Professor 𝐕𝐢𝐥𝐤𝐨, and then we will follow with my presentation focus on spark ablation technique as a building block for gas sensing developments, and we will conclude with some QA session. Please take into account that this video is recorded and will be shared at the end of this presentation. So now we can move on, and I will start with a brief introduction about VSPARTICLE. So VSP is a Dutch high-tech company located at Delft that is developing innovative technology for nanoparticle production and deposition. Essentially, in a nutshell, VSPARTICLE nanoparticle generators and printers enable researcher and material device manufacturer to synthesize and deposit nanoporous materials in an easily, clean, and efficient way. So now we will talk about today's presenters. So for me, it's a great honor to introduce Professor 𝐕𝐢𝐥𝐤𝐨. He is an associate professor at the University of Zagreb. He has founded the film FIB laboratory, and he's current research, let's say, in a lot of nanomaterial related topics. And I think his own research is to get a better understanding of the material science, to then get a better understanding and to optimize different devices in a wide range of applications like energy storage devices, sensing devices, and even for space applications. So he has a very good background in material science. And he published in numerous peer-reviewed journals, and he has patents. So he has a very large background in the material science community. From my side, I'm Leandro Sacco. As I told you before, I'm application specialist nowadays at VSP. I have a background in physics. I carry out my PhD in France at the École Polytechnique. And along my careers, I always work with nanomaterials, especially with carbon nanomaterials like nanotubes, graphene, and carbon nanofibers. And yeah, during the last 7-8 years, I was intensively working in the development of gas sensors. So that is basically my background and my skills. So now, before start with Ვილko presentations, we would like to have some interaction from the audience. So we will run a quick poll. So please take a few seconds to answer these questions so we can have your insights. So the first question is, how familiar are you with spark ablation technology for nanoparticle production? So take your time and then shoot, please. We are gathering your replies. So very interesting feedback. So it's quite balanced, I will say. Thanks a lot. So now it's time for Ვილko. I would like to highlight anyway that Ვილko presentation is recorded, but he will be here at the end of his presentation and my presentation, actually at the end of my presentation, to reply your question in the QA session. So now we can move forward to Ვილko presentation, and for me it's a great honor and pleasure to give the floor to Ვილko.
Well, hello there. I'm Ვილko Mandić from Faculty of Chemical Engineering and Technology, Zagreb, Croatia. So at that part of the world, we are actually doing something with sensors. And therefore, I would like to welcome you on this webinar. I'm not going to read the main title, but I'm going to say that we are going to hear something about new materials developing routes applicable for gas sensors. So let's dig in. What we're actually going to hear, we're going to hear something about infrastructure and background from preparing functional thin films. We're going to say something about how to prepare these films with spark plasma ablation deposition, or commonly known as nanoparticle generator. And I'm going to maybe spend most of the time talking about nanostructuring and non-stereometric oxides as something in between of the, let's say, broad phenomenology that is very interesting for various aspects, but as well as gas sensors. So we're going to say something about utilization of that in gas sensors. And I guess that in the end, if time allows, I'm going to put that into perspective with respect to basically additive manufacturing. And let's start. So I'm not going to scare you away immediately with a very broad slide, but the group is dealing with something. And in the agenda group, there is also a mention of sensors. So I guess I'm not here accidentally. What else does the group do? And I'm kind of going to just wrap it up that we're dealing with broad range of nanomaterials. And some of the nanomaterials are applicable for environmental materials and for energy conversion. And this is maybe the main agenda of what we think is going to bring us new projects and money and fame and everything else. Of course, being at the chemical engineering faculty, there are also a lot of other departments and colleagues and interests in terms of material development, design, and characterization. And what the group actually is, because that changes, I'm not sure, but I will say this is up to 10 of doctoral and postdoctoral students. And if you want to join the board, send me an email. You can probably find it, or you can find me as well. And that includes some kind of publications, which I can probably facilitate. And, so actually, let's dig in how to prepare, or what do you need to prepare something. So being, again, a chemical engineer and having an experience in our expertise in chemistry, I have to start with something that I consider to be very simple. And this is just a general solution chemistry thingy. And by that, I think that I'm talking about like a wet chemistry method, salt gel synthesis, and etc. So this is like a prerequisite to actually go further. And when I say further, then I'm talking about organization, self-organization, or kind of allowing additional phenomenology in the constituent domains. And that is also kind of a simple. If you have luck, you have a good system, and good system is basically putting something favorable into chemical batch reactions. And I'm going to talk about that a little bit more later. So if you want to go more expensive, and we are curious, we want to go into more expensive and more demanding setups. Then you play with physical deposition, and physical deposition basically presumes for us something like Mach sputtering or evaporation methodology. And we also found out that spark ablation or kind of a plasma discharge phenomenology or methodology exists or kind of allows performance of the materials that we're developing in between of those two techniques. And this is very interesting, and in good and in bad way. And of course, we need various post-processing. Not everything can be done from the first. So we have various let's say oxygen, ozone, plasma, and kind of a supercritical fluid thingy to go after. Okay, so, and that's basically what I just wanted to say. There is also a characterization importance. So whatever you do, if you cannot see it very well, as if you have not done it. So for that, we utilize basically a broad range of spectroscopy, dedicated spectroscopies through the electromagnetic spectra, and of course, diffraction and scattering techniques, and of course, applied electrical and optical characterizations. Why that? Because we need kind of a diffraction to allow us observing of the structure of core of the materials, which are preferably sometimes crystalline. So that's how diffraction works, but also to kind of explain the domains or their organization. And we do want to talk about nanostructuring, so this is relevant. We need high brilliance methodology of the synchrotron facilities for 𝐏𝐫𝐨𝐍𝐢𝐜𝐈. So scattering of X-ray scattering of basically thin films and how to actually prepare something. So when we go in the direction of the methodology in between of what I have said, so between Mach sputtering and evaporation, we go with spark plasma ablation deposition. So basically we bring two electrodes very close, and then upon kind of putting a charge on them, a spark happens. So discharge occurs, and discharge takes a toll at the electrode. So basically a part of the electrode is ablated into a plasma, which then cools down, condensates, and forms primary particles, which can then simplified grow and eventually aggregate and agglomerate. So by having, let's say, a good idea when to engage in that, let's say, evolution of the particles, we can have from very small nanoparticles to greater, and thereof we can kind of tailor which kind of system in terms of morphology, of course, composition as well, we can prepare or maintain them. So we have also a selection of various reactors to help us on that. And this is basically a diffusion, filtration, and impaction reactor. So I'm not going to waste time on everything else, which is also interesting, just not enough time. But I'm going to talk about mostly impaction. And eventually I'm going to say that even the printing is even better. So if you look left, basically you have various options in terms of how to put electrodes together, and in terms of where the flux or the carrier gas goes. So we can create gradients, and the more electrodes, we can create composition gradients and kind of a core shell phenomenology and everything else. But first things first. So this is the setup that we have in the laboratory. It's not complete because I've just made a very unclear picture, but basically we have two spark plasma generators or nanoparticle generators and a cascade of MFCs that allows basically modification of the carrier gas. And why would we like to do that? Because actually we're not so interested in just nanoparticles of, let's say, metals. And we want to really go in the direction of metal oxides. So we play with the atmosphere. We make the inert atmosphere reactive. And that's just kind of an onset of all of our interesting stuff and all of our problems. So some of the problems can be kind of tailored for the benefit of gas sensing, as well as some other aspects. So let's say that aspect of, which is kind of maybe even more fancy than gas sensor, is aspect of solar cells. And obviously, if we just wait for even less than 100 years, just 70 and something years, obviously that kind of material or that system is going to be very relevant. So we are looking into future technologies. We just want to make or utilize the materials that we're preparing for the technologies that are going to be relevant. And of course, solar cells are easier said than done, but we're trying. And very similar to that are also, just one more sentence. There are a lot of solar cells, but this direction or this area or this thin film emerging solar cells are those where the materials that we can prepare can be heavily utilized. And I wanted to say that basically not so different are batteries, not so different are supercapacitors, and not so different are sensors. So all of the semiconducting materials kind of blend into kind of a joint story for better energy efficiency. And kind of how to do that, we have to optimize something. So of course we can play with computational design optimization, with the synthesis procedure early stage, and of course things are not done perfectly in the beginning, so we can play with post-processing of various aspects. And by all means, if we don't know what we have prepared in terms of characterization, then we're nowhere. But the main part is play with the modifications of constituents and of the devices. Both of this is relevant for our nanoparticle generator. And I'm going to talk more about nanostructuring and as a morphological aspect of the story, and non-stoichiometric oxide as a chemical part of the story, so composition-wise. So here I have a scheme of titanium nanotubes, and we have prepared them by modifying the conditions. Obviously, some conditions, and here we basically just modified, let's say, the onset, so the seed layer, give rise to very different layers or orders. Some of them are very nicely ordered, let's say perfectly ordered, and some of them are disrupted. And this is what we want to bring into the game and control. And that's just a scheme, but how to do it is just utilize, again, from the beginning, chemical bed reaction. We find a favorable media and favorable, additional anodization, so let's say electrochemical etching moment, and that is sufficient to kind of allow over various, let's say, intermediate phases, titanium hexafluoride to be specific, growth of the titanium nanotubes. I'm just going to cut things short. The same thing, but in different media, is allows the growing of rods for zincite, etc., etc. So in doing so, we actually encounter a lot of problems, defects of various kinds, but it seems that these defects can work for us and not against us if we know what to do with them. So basically, I'm talking about implementation of nanostructured and substoichiometric materials for gas sensors. And that can have immediate advantage that, of course, arises from the large specific surface area. But can have also a specific advantage which arises from the reactive nature of the diffractious layer. Basically, just the rate of reaction is faster for these kind of materials. From the morphology point of view, so our deposition method can be utilized to prepare porous film that behaves similar to nanostructured films. That's fine. But we can also kind of think in advance and prepare seed layers that cannot be very easily prepared by other methods, and then grow the nanostructured materials in specific way from the specific seed films. So again, this is a very good agenda, and to confirm that, we actually have done it, and we have grown various aspects, and we have described the nanotubes or nanotubular formation with various aspect ratios using Jesus methodology. So obviously, seed layer are important there, and that, of course, is kind of I'm just going to say, interplay of how things evolve, assemble from the moment of, let's say, which I said, when to engage, which size domain to engage in terms of aggregation versus agglomeration. Okay, so what does that contribute to sensors? Of course, there are various aspects of sensor, but I'm going to talk about conducting sensors, so I'm going to catch that moment just in a second. So here, I'm just going to talk about oxides, and these oxides that we can observe are really relevant in terms of composition. So obviously, that substoichiometry is monitored or reflected through the various level of defects of the structure, and just kind of, from the AFM, TEM, and various spectroscopies, just trust me on that, we have been able to observe that. And I'm just going to browse to that and basically say that we can have another concept here, which is basically kind of a extrapolating through the concept. So decoration, filtration, and impregnation are the concepts that kind of are even more utilizable for the photophotovoltaic sensors. So the immediate advantage can, of course, arise from large-scale and homogeneous modification that are kind of delivered by the nanoparticles, performance boosting nanoparticles. So the other aspect is environmental and economical advantages that just arise from the modifying particles just on behalf of their nanosize. So how do we play with that? So we can utilize the method to basically disperse them across the desired surface without any, let's say, deformation and penetration. 1 point. Then we can really impact them and make real films of the material that we're depositing without deformation, with deformation in the films. So basically make thin films, but without penetration because we use a material that is not really soft, so basically hard material. If we use soft materials that we can penetrate into them and make a shallow layer of, let's say, modified properties, and normally that would be kind of a polymeric material. If you want to go deep, then there is interplay with diffusion, so we can have a spontaneous one, or we can overcome it and kind of force diffusion, and that's what we would like to do with supercritical fluid. So here I have an example of actually a polymeric rod, and what we have done, printed out the rod. So okay, this takes a long time, but it's a nanorod still, and we have pushed the metallic nanoparticles into them. So basically, we made sensing rods from just printing and modification. I'm just going to talk about cellulose because this is, for example, in contrast to previous method, super easy to make. So you can make a large-scale cellulose without, spending days and nights on the printing machine. And obviously, you can see that the morphology of the cellulose can also kind of open up for everything. So it can be a carrier. One other thing that kind of a cellulose carrier can have is, and I'm just going to skip the synthesis, is ability to react with water. So basically cellulose is swelling, and that kind of a swelling or water is basically conductive, means that that kind of material inherently is suitable because of the electric conduction to serve as a sensor. And that's fine, but we want to kind of engage it even more. So modify that material again with our SPAD method by utilizing the opportunity to create quantum dots. So basically, small nanoparticles can behave as quantum dots. Quantum dots are photovoltaic, and thereof we have quantum dot cellulose sensing material, which is inherently a photovoltaic device, which is basically an energy autonomous sensor. Interesting, I would say. So, okay, we also characterize that the quantum dots is not a mistake, that really quantum dots exist. There is cadmium selenide. And then we actually characterize the selectivity and sensitivity, or basically sensing performance in a reactive reactor for humidity cell using solid-state impedance spectroscopy, which is a super powerful and very great method to kind of monitor what's happening with the charge carriers on all aspects, which is also modelable, and kind of that is what we prefer. It's not super fast, but it's thorough. Yeah? Okay, and in a nutshell, all of these features that I've been saying for a solar cell are, and I think I mentioned that already, can be really utilized in gas sensing photovoltaic system, but as well various electrical and photocatalytic systems, battery and pseudocapacitors, and generally just any semiconductor system. So basically, by doing that, you're doing everything. And I have said that by doing that, we actually made energy independent sensors. Very simple. So what would make me happy? So how to move forward? So in terms of moving forward, we would like to kind of go with the printing setup. So what we have done is just kind of created dots. But if you have a printer, then you can create surface. And of course, this is also very interesting from various aspects. I'm just gonna not go in various super obvious aspects of why sensor films or why printing films is great, but I'm just going to consider a dot. So we have a very, where is it? A very dot, which is kind of a reference. We start with printing from here. And that dot, okay, it's there, actually can be very useful for flash DSC characterization. So basically, you sometimes have very difficult time to make amorphous metals or metal glasses. And you can, if you do that in a precise way and you can print in a precise way, then you can have, again, a sensor, but basically this is a thermal sensor. So I'm just gonna utilize the sensor, but in a completely different direction. So that would be possible with printing. That is possible with printing. So of course, and okay, to be a little bit critical, what happens when you actually have a discharge of the spontaneous type? You don't know that what happens is going to happen at the same rate, at the same time, cold, warm on various aspects of various elements. So to kind of force what you want to do, you have to implement a waveform generator, and then you would have basically a forced discharge or basically a controlled discharge. So this is something to kind of consider, to have really potent material that is really suitable for deposition between the evaporation, between the magnet sputtering, with broad envelope of composition, of configurations, and kind of a deposition strength. So I'm not sure how I'm with them, so maybe I'm gonna cut myself away. But I will just say that, let's say, the importance of, let's say, nanostructure is I would say the main thing in terms of scientific approaches to handling various systems. And I would say that for gas sensor, that kind of is the same thing. So we have to kind of find the bottlenecks to resolve material science problems. And I guess that this device or potentially even printer are going in the direction of opening these kind of opportunities. And by that, I'm just going to say thank you, and I'm open for your questions. Thanks.
So thanks a lot, Filko, for this insightful session. So to all the audience, I would like to point out that they can make the question in the chat and we will reply in the QA session. But now it's time for another poll session. So here will be display the next question. So please feel free to vote. We would like to receive your feedback. So the next question is, what method are you mainly using to deposit your gas sensing layer? You can select all these options. So take your time. So we have the replies that are evolving with time, but spark ablation is quite popular in the audience. So that's very nice to hear. Okay, so thanks for your interaction. And now we will start with the second part of the webinar that basically will be focused on gas sensing application based on the spark ablation technology. And yeah, basically in this presentation, we will cover different aspects of the spark ablation, not only on the nanoparticle generation, but also at the nanoprinter point of view. What are the capabilities and possibilities of this technology? And then we will go to a concrete example in this case. So we will show some examples or print zinc oxide lines that we use as a gas sensor. So that's our, and we use it for toluene sensing. And yeah, at the end of this presentation, we will highlight the most remarkable results. So then I want to start first with this presentation with a question, and basically a valid question is, why do we need to improve our current gas sensor technology? And this is a valid question, especially when you take into account that metal oxide semiconductors-based gas sensors were dominating the gas sensing market during the last 70 years. So essentially, metal oxide semiconductor gas sensors, there are chemiresistors that they are basically, we are applying a potential and we monitor the changes in resistance with the interaction of a gas target molecule. So basically we track this resistance variation, and then we track a calibration curve, and we can predict a gas concentration. These devices, they are working relatively okay in certain conditions, but when you want to really shift from these operation conditions, they start to struggle. An emblematic case is when they start to think, why not to integrate a gas sensor in a smartphone? And the challenge here is not only related with how we integrate with the size of the device. We can do really small devices, but we also need to improve a lot of key figure of merits regarding the gas sensors, such as the sensitivity, the selectivity, the power consumption. The power consumption is also very important for when you want to deploy a very high dense grid of sensor. For instance, in a city, if you want to deploy sensors along the city, you don't want to change the battery of your sensor once a month, not even one a year. You want your sensor operating constantly. So there are many aspects that we need to improve regarding our current technology. Also, we need to decrease the limit of detection. We need to improve the reliability. And then there are some characteristics that maybe we need to improve for some specific application fields. There are sensors that need to work at very high temperature, harsh environment, like high pressure, high radiation. And the current technology cannot provide solutions. So there is a common agreement across the material science community that in order to overcome all these problems, nanomaterials is an attractive platform. And many researchers were working during the last decades with a wide range of nanomaterials, ranging from carbon nanomaterials, metal oxides, nanoparticles. So there is a large menu of nanomaterials where you can build your active sensing layer for your gas sensors. So that is why also the nanomaterials are an attractive material, is because, as Vilko mentioned previously, they provide a large surface to volume ratio, and they are easy tunable. So you can really tune the materials, and that are essential requirements in order to develop the next generation of gas sensors that will fulfill the requirements of novel applications. So also I have another question, is does the nanoprinter and the spark ablation technology can fulfill these requirements? And of course, now we will stop asking us questions, and I will try to give you some facts and some insights about the spark ablation technology, so you can really, at the end of this presentation, have a better understanding of this technique and how the spark ablation generation and the nanoprinter couple, they are a powerful tool to develop your gas sensing layers. So to give some more context, I would like to point out what are the methods involved typically in a gas sensor fabrication. Here we will focus just in the sensing unit. We will not take into account the readings and data communication, classification. We are focused really in the heart of our sensor, the sensing unit. So typically we start with a substrate that is MEMS, could be a MEMS, NEMS, it could be a microheater, where then it's fabricated by conventional techniques like CMOS compatible. And on top of that, of course, this is not the only way to do it, but typically then we deposit the sensing active layer that, it could be also by means of these CMOS compatible techniques, but mostly of the nanomaterials, they need some post-CMOS deposition, like CVD for the synthesis of nanotube or graphene. It could be spray pyrolysis, electrodeposition. There are a lot of wet chemistry approaches that you can deposit, and even the spark ablation with the nanoparticle generator. But it's important to point out here that all these methods, they are not localized. So we cannot really select the area where we want to print. And that could be a very interesting feature regarding gas sensors, because with gas sensors, sometimes we want to do arrays. And sometimes we need to functionalize different sensors in the same platform. So these techniques like localized deposition, like inkjet printing or aerosol jet printing, are capable of this. And then the spark ablation coupled with the nanoprinter also can do this. And what is very important here to highlight, that we can not only do the deposition of the sensing active layer, but also we can functionalize our device. So Vilko also mentioned the flexibility of the nanoparticle generation. So here are basically all the materials that we can use in spark ablation techniques. So basically, they are all conductive and semiconductive electrodes. So we have a large menu of materials that we can use. And also Vilko mentioned there are many combinations that we can use. If we have one generator, even we can use the electrodes with the same material, or we can mix electrodes. We can use alloy or sinter electrodes to get sintered nanoporous layers. And of course, the flexibility is higher even if we couple two generators. That it could be even better, depending on the requirements of the material that you want to deposit. But imagine that we are not limited by the number of generators. Here is the example how we connect these generators to a printer. In this case, you can observe two generators, but it could be also 1, 3, 4, or 5. So then the diversity of material that you can deposit is really depend on the number of generators. But what I really want to stress is, like, already with one generator, you can deposit a large amount of material combination. So here I want to give you some insights about the nanoprinter. So here on the top of the tool, you can see the nanoprinter generators that create the nanoparticles and in an aerosol. And then we collect this aerosol and it's flow to the vacuum chamber, where we have a nozzle and we have a software holder that can move in the free direction. So we can easily run a script to create patterns of deposition. So that is very interesting feature of this tool, because you can run your script and leave your sample and that will be printed. So you don't need to really babysit the tool. And here you can read some characteristics of the nanoparticle depositions. What I really want to point out here for the people working in the gas sensing community and in generally across the material science community is that this process is fully dry. So you don't have any wet chemistry involved. So that can be very useful, and it can be very useful, yes, in terms of reproducibility of your deposition. But it could be very convenient. And then, since this process takes place at room temperature, you don't have to worry about the thermal budget of your substrate. So you can do depositions in flexible polymers. And regarding the size, up to 6-inch silicon wafer can be loaded. So that are very interesting properties, and also a specification that match with the requirements of the gas sensing technology. So now we will talk about some specific examples, so you can see how powerful and how reliable is the tool. Here we can see a set of lines that we print using zinc electrodes. So then we deposit zinc oxide material at different powers. So essentially, with the nanoparticle generators, you can control 3 parameters, I will say, in principle, like the potential, the current, and the gas flow. So here we just change the power. So as we increase the power, we expect to have more material deposited, and then we deposit 5 identical lines in these substrates, and then we measure the thickness of this material. What is important here, I can give some details about the procedure, because essentially we cut with the silicon diamond the silicon substrate, silicon oxide substrate, and then we did some cross-section with a SEM, and we measured the thickness of these lines. So here are 2 things. You can see that the addition is very good, because the lines survive after we cut the wafer, because we observed that in the cross-section SEM. And also we measure the thickness variation of these 5 lines, and we observe that the reproducibility is relatively high, because we have less than 3% variation between the thickness of each line. And also we did some thickness calibration, because essentially we print in the same position that in another substrate, of course, 2 passes, 4 passes, up to 8 passes. So basically we build up on a line and we measure the thickness. So with these 2 parameters already, you can get a very good indicator of the reproducibility and how you can calibrate the thickness of the material, the layer that you want to deposit. Another parameter that you can vary is the speed of the holder, and in that case you will deposit less material. And if you are interested about the thickness, if you go the software holder speed is very high, the printing speed is high, you can deposit just a sparse nanoparticle, like cluster of nanoparticle, and that would be very interesting for functionalization, for instance. But if the speed is relatively slow, then you can build up a layer, thickness layer, and you can print up to 100 microns or 200 micron thick layers. So the range is quite large, because you can go from few nanoparticles up to 100 microns. So then what we did is essentially to take these lines, and we print lines in a 4 electrode configuration device. We did some annealing to be sure that we will get the zinc oxide, but if you don't want to anneal, you can also introduce in your flow oxygen during the spark, the nanoparticle generation, in order to oxidize your material. But it's also important to point out that this material is so porous that as soon as we remove it to the atmosphere, they will oxidize. And then after the annealing, we proceed with the electrical measurements of the device under the exposure of toluene. And so all the gas sensing measurements were carried out at the material center Leuven. So there you have the link if you want to see some specification of the gas sensing setup. So we were ready then to measure the response of our devices towards toluene gas molecules. So in the left, you can see the resistance variation of our device. So during the first 30 minutes, we let the device to stabilize, and then we expose up to 5 ppm of toluene. We left the flow again dry air, and then synthetic air, and then we expose up to 10 ppm of toluene, and we did the same protocol up to 20 ppm. So essentially, with this kind of experiment, you can extract your calibration curve of your device in terms of the response. So we compare the resistance at the baseline and when at the maximum response of our device. So in the right, we can obtain the calibration curve of the device responding towards toluene, and we did this with 2 devices. So you see device 1 and device 2. They have very similar behavior, and of course we expect this behavior because essentially the thickness variation is very low between the lines that we print. So this is a very good indicator for the reproducibility purposes. And from this curve also we can extract the sensitivity of the device and the limit of detection. And in this case, the limit of detection is around 1 ppm, so 1 part per billion. And this we are very proud of these results, because if we compare with the existing literature, we observe that this limit of detection is very good, is around 1 ppm. But what I really want to point out here is that still there is a lot of room for optimization. And here we just print some lines and we use it as a gas sensor. And already we are among 10% of best sensors reported in the literature. So this is a very promising result. And of course, there are a lot of room to improve this kind of sensors. So now, I will highlight the most important aspects that we cover in this presentation. So I hope that I convince you, or I give you enough evidence to show you that spark ablation coupled with a nanoprinter is a very suitable deposition technique for the gas sensing applications, and it's very straightforward, and we gain some insights about the reproducibility. Here we show that if we print different lines at identical printing parameters, the variation is below 4%. This is reflected also in the gas sensing performance of these devices. They were very similar. And of course, as I mentioned before, there's still a lot of room to improve, because we can functionalize this device to be more sensitive to toluene if you want. We can deposit some catalyst, for example, or we can tune the parameters involved in the spark ablation in order to get a higher porosity or a smaller nanoparticle size. We can do different kind of oxidations. So there are a lot of room to improve this kind of devices. So to finalize my presentation, I want to inspire you, both the newcomers in the field and experienced researcher working across material science and gas sensor, to do your own spark gas sensor based on the spark ablation technology, and even you can try to fully print your own device. But what also is important here to point out is, like, even if you are working with another kind of active sensing layer, like it could be an other kind of nanostructure like graphene or 2D materials or carbon nanotube, you can use this technique to functionalize and to give the flavor that you want to your nanostructures. So that's also the beauty of this system, that we can not only deposit the active sensing layer, but also we can functionalize. So then at the end, I want to give a special thanks to all the VSP members, and of course all the people that make possible this webinar, a lot of experts, and also to Minsu that prepared a lot of these samples, and also Filiberto Ricciardella. So thanks to all the team, and now we will go to the last polling. And of course, don't hesitate to put your question or any comments in the chat. So the last Q8 is, will you be more interested in using the spark ablation technique to deposit a base material, or to functionalize, or both? So thanks a lot. So now we are officially ready to go to the Q&A session. So we have a question. It is for Vilko. So excellent first session. I'm wondering if you have used a spark ablation made nanomaterials for biomedical application, and this question is coming from Shakib. So Vilko, the floor is yours.
So, like, there's my main advantage is basically that I'm originating in between of physicists and chemists, but that does not really extend to the biomedical part of the scientists. So by all means, I would like to kind of engage in that direction as well. For sensing, that has not been done yet, but for various other aspects, yes. So ablation has not been, or this methodology has not been fully implemented in this direction, but kind of a very straightforward answer is that all of the nanostructured features, especially all the growths or the kind of formations or nanoformations, are very size dependent to serve as a carrier or for various signal sensitivity response to various features. So combining it with biomaterials is very interesting and very much possible. But sure, it was also implemented with cells. So, for example, for titanium materials, it actually has been proven and investigated which size domain of the nanoformation is favorable for proliferation and such, let's say, aspects. So by all means, do engage, find me, and we can try to investigate more on these aspects.
Okay, Vilko, thanks a lot for your reply. We have more questions from the audience. So we have one question that is from Shatibashya. It is possible to deposit carbon nanoparticles using spark ablation? If yes, kindly share some insights. Yeah, of course, it is possible to deposit carbon. We can use carbon electrodes, and then you will get a similar deposition. Of course, then you need to optimize depending on the sparkling parameters depending on the size, distribution. If you want a compact layer or you want more like a dispersed distribution, but definitely it is possible to deposit carbon nanoparticles. I hope that I reply your questions. And then we have another question from Thomas Namak. Have you ever tested any spark ablation nanomaterial for hydrogen sensors? Yeah, we are working with several projects with gas sensors. We have some industrial partners also. Specifically for hydrogen sensors, to the best of my knowledge, we didn't work yet, but of course, it could be possible to do some test of hydrogen. Definitely, there are many. All the materials that in the literature are using for hydrogen sensors, they can be used here in terms of, as I mentioned before, like decoration of the sensing active layer, or just to build up your base materials. But it is compatible for sure. So thanks for your question, Thomas, also. I think we have place room for a few more questions, but of course, I would like to point out that if you have any question that later on, you can always contact us, and we will take the time to reply your questions in the future. So don't hesitate to contact us, and we'll always interact with you. So we have one more question for Professor Željko Mandić. Again, how a spark ablation facilitate the growth of order arrays? Željko, your time.
Basically, I have to have 20 minutes to answer that. But in a nutshell, of course, you can vary various parameters during the processing that actually grows nanostructures. But before that, it's very important what do you use. And normally, let's say the envelope of materials that are used for seed layers is very narrow. But just on behalf of the fact that, as I said, this is a very versatile method, you can really have a variety of not just sizes, but also shapes or configurations of the nanoparticles that you use for seeding the growth of nanostructured arrays. So by all means, utilizing that variety can really broaden the aspect of how you can, or to what extent you can grow and tailor such ordered arrays.
Thanks a lot, Željko. I think we have time for a last question. So what is the additional benefit of using nanostructured materials in comparison to just using nanomaterials? Very interesting question.
Well, yeah, basically the 1 or 2D phenomenology adds to additional functional performance. Just one example, this is the directionality of the growth. So basically that allows selectivity in gas sensing and basically is, as I said, another parameter to the benefit of functionality and performance of material in comparison to, let's say, isotropic nanoparticles, just porosity, which would not allow such, well, to an extent, such performance.
Thanks a lot again, Željko. So we will reply the last question here, but once again, don't hesitate to leave your question here in the chat or just contact us by email. So the last question is, Dr. Žago, besides the functionalization, is it possible to form a composite material where the catalyst is within the base material instead of being deposited at the surface? So yes, this is a very nice question, and thanks to ask, because that is another possibility of the spark ablation. Instead of doing a conventional decoration where we have our base material and we deposit on top, if we have two generators, or even with one generator with two different electrodes, we can create a spark where all the aerosol will be mixed, and then we will deposit this on our substrate. So this is a different configuration where we will have mixed material. It will be a kind of composite. So this is very different, like the conventional functionalization, and it's something definitely very interesting to explore in the gas sensing field. So I think that we have a lot of interaction with the audience. It was very nice to reply of your question. I will like to thanks again to Professor Filko for all your time and your very interesting presentation. And I would like also to thanks to all you, the audience, to attend into the webinar, and also the webinar will be shared soon. So thanks a lot once again, and we keep in contact.
Ciao.
Bye-bye.